Hello dear students, welcome to the next part of the chapter solutions. In our last video we have studied two colligative properties, that is relative lowering of vapor pressure and elevation in boiling point. Today we are going to study our third colligative property, depression in freezing point. First of all, what do you mean by freezing point? Freezing point is the temperature at which the solid state of the solvent coexist with liquid state of the solvent. Or also I can say that it is the temperature at which the solid and the liquid state of the solvent, they are in equilibrium. I will try to explain you this with the help of a graph. Here you go. So when you have plotted the graph of vapor pressure against the temperature, this curve represents the solid state of the solvent and this curve represents the liquid state of the solvent. Now as you can see in the graph, this is the point at which the solid and liquid state of the solvent, they coexist, and therefore this temperature will be the freezing point of that solvent, TF0, indicating the freezing point of the pure solvent. Now when we add a non-volatile solute to this liquid solvent, we know the vapor pressure decreases. As a result, the curve will go like this. Now this curve represents that of a solution. So now this is the point where the solid and liquid phase are coexisting, and therefore this will be the freezing point of the solution. We can say also that the vapor pressure at which solid and liquid phase, they have the same vapor pressure, that will be called as the freezing point of the solvent. Now from the graph, as you can see, the freezing point of the pure solvent is greater than that of the solution, and the difference between these two will be called as del TF. So we can calculate del TF as TF0 minus TF. I will give you the example of depression in freezing point. What we have discussed, that when we add a non-volatile solute to the solvent, its freezing point decreases. For example, all of you know that the water, its freezing point is 0 degrees Celsius. But when we add 342 gram of sucrose to 1 kilogram of water, the freezing point drops to minus 3.5 degrees Celsius. That means when sucrose as a non-volatile solute is added to the solvent, the freezing point will be decreased by 3.5 degrees Celsius. The water will not freeze until and unless the temperature goes to minus 3.5 degrees Celsius. This is what is the meaning of depression in freezing point. Now coming back to this equation, del TF equals to TF0 minus TF. In this, what does TF0 represents? TF0 represents the freezing point of the pure solvent. TF represents freezing point of the solution. Okay. Last time we have seen that del TF is directly proportional to molality. So introducing the proportionality constant, del TF equals to Kf into m, where Kf will be called as cryoscopic constant or molar depression constant. As we have seen that Kb, we have seen that in elevation in boiling point, Kb is different for different solvents. Similarly, Kf is different for different solvents. The SI unit of Kf is same that as of Kb we have studied. So SI unit of Kf is equal to Kelvin kilogram mole inverse. We can also write the SI unit of KF as K into molar. Now how can we define KF? From the formula we can say KF is the depression in freezing point of 1 molar solution, or it can be defined in other way also. The other way of defining KF is depression in freezing point when 1 mole of non-volatile solute is dissolved in 1 kilogram of solvent. Now del TF equals to KF and its molality, and therefore we will replace it by its formula into WB into 1000 upon WA into MB. Rearranging this equation we get MB equals to KF into WB into 1000 upon WA into MB into del TF. So this is the formula based on which we will have a lot of numericals. The numericals based on colligative property will be always of 3 marks. Now in this formula, MB represents the molar mass of the solute. KF, I have already told you that it represents cryoscopic constant. WB represents mass of the solute. WA represents mass of the solvent. And del TF represents depression in freezing point. So overall, what is the summary of this colligative property? That whenever we are adding a non-volatile solute to the solvent, the vapor pressure decreases. As a result, the solvent gets freezed at lower temperature. Why we are studying these colligative properties? Because they have applications in our daily life. So what are the applications of depression in freezing point? The very first and the most important is anti-freeze mixture. This point is very important. So many times this point is asked in board exams in the form of give reason question. Now this anti-freeze mixtures, these are used in cold countries, and this phenomena is based on the depression in freezing point. Ethylene glycol is one of the example of antifreeze. Now when ethylene glycol is added to 1 kilogram of water, the freezing point of water is lowered by 10 degrees Celsius. That means water now freezes at minus 10 degrees Celsius. Now how it is used? Now this phenomena is used in car radiators. The radiator fluid is a mixture of ethylene glycol and water, where ethylene glycol acts as a non-volatile solute, causing the depression in freezing point by 10 degrees Celsius. Now this is used in hilly areas where there is a heavy snowfall. Now what happens due to heavy snowfall? The fluid in the radiator gets frozen, and that gives hindrance to the working of the vehicles. So if we are using this antifreeze mixture, the radiator fluid do not freezes even if the temperature falls till minus 10 degrees Celsius, and therefore vehicles can be operated very smoothly. Second is road salting. Again, in the hilly areas, when there is a heavy snowfall, the roads get blocked, and therefore it is very necessary to clear the snow on the roads. Now how the snow is cleared on the roads? By using sodium chloride or calcium chloride. Now this sodium chloride or calcium chloride act as a non-volatile solute, and they bring the depression in the freezing point of water to such an extent that water cannot freeze easily to form ice, and therefore it easily helps in clearing of the roads. So let us start with our fourth colligative property, osmotic pressure. But for that, first of all, we must know what is osmosis. Suppose I have taken two containers which are interlinked by semi-permeable membrane. Semi-permeable membrane is also called as a selectively permeable membrane, as it allows the movement of only particular solvent molecules. Now in one container, I have filled it the solvent, pure solvent, and in another container I have filled the solution. Now these two containers are, although interlinked, they are separated by semi-permeable membrane. Now when I fill the solvent and solution in two different containers, there is a movement of the solvent molecule towards the solution side, and that is what we call as osmosis. The phenomena of the flow of solvent molecule through a semi-permeable membrane from pure solvent to the solution is called as osmosis. I can also say it as, it is the movement from low solute concentration towards high solute concentration, and that phenomena is called as osmosis. In your junior classes you have studied diffusion, which is a similar phenomena of this, but there is a difference between osmosis and diffusion, that in diffusion we are not using semi-permeable membrane. Now semi-permeable membrane can be natural or artificial, for example animal membrane, parchment paper. These are the examples of semi-permeable membrane. So in osmosis there is a flow of pure solvent molecule towards the solution side. Now if I apply certain pressure on this solution side, the flow of solvent towards solution side will stop, and that is what we call as osmotic pressure, which is indicated by pi. So the minimum excess pressure that must be applied to a solution side so that the flow of the solvent molecule towards the solution side is prevented is what we call as osmotic pressure. Let us see why osmotic pressure is considered as a colligative property. There was one scientist, Van 't Hoff. He said that pi, that is osmotic pressure, is directly proportional to Ct, where C represents the concentration of the solution and T represents the temperature. Introducing a proportionality constant R, which is a gas constant, the equation becomes pi equal to CRT. Now this concentration is taken in terms of molarity, and therefore the equation changes as pi equals to number of moles of solute upon volume RT. So rearranging the equation, we can get the molar mass of the solute Mb equals to Wb upon pi V RT. Based on this, you get the numericals. Now in this equation, pi is directly proportional to concentration into temperature. Generally all the experiments are carried out at room temperature, which is a constant one, and therefore I can say the osmotic pressure is directly proportional to concentration. And concentration means what? The amount of the solute, and therefore the osmotic pressure is called as colligative property. Now depending on osmotic pressure, there are three types of solutions. The first one is isotonic solution. Isotonic solution means two solutions which have same osmotic pressure. I can say pi 1 equals to pi 2, or I will say C1 RT equals to C2 RT. If I take the ratio of these two, pi 1 upon pi 2, this become equal to C1 upon C2, as RT being constant one will get cancelled out. Now again this is the formula based on which you have a lot of numericals. The second is hypertonic solution. These are the solutions having higher osmotic pressure than the other one. Third is hypotonic solution. These are the solution having lower osmotic pressure than the other solution. As we have seen the application of freezing point in daily life, we are now going to study the applications of osmotic pressure in daily life. The first example which I have discussed is again a very important one. So many times the question is asked as a give reason question, that why the medicines are mixed with saline water. Saline water is nothing but 0.91% NaCl solution when they are injected into our bodies. Now 0.91% solution of NaCl, which is also called as saline water, is isotonic with fluid inside human RBCs. That means it 0.91% solution of NaCl and the fluid inside the RBC, they will have same osmotic pressure, and therefore there will be no impact on RBCs As a result, the medicines which are given in our body, they will not harm RBCs, and therefore all the medicines, they are mixed with saline water or 0.91% solution, NaCl solution. Now what will happen if the concentration varies? If the RBCs are placed in a solution with salt concentration less than 0.91% solution, now this saline water will become hypotonic for RBCs. The water will flow into RBCs and the cells will swell up. As a result, they will burst. Let us consider the reverse situation. If the salt concentration is more than 0.91%, now the solution will become hypertonic. Now whatever fluid is present inside the RBC, that fluid that will flow out. As a result, the RBCs will shrink and RBCs will collapse. So both these conditions are lethal to us, and therefore all the medicines, before they are injected in our body, they are mixed in saline water, that is 0.91% NaCl solution. Here are some more examples of the applications of osmotic pressure. You must have seen the mango pieces when they are cut or put in the salt solution before they are converted into pickle. They are of large size, but after a few days they shrivel and they become small in size. Why? Because they are placed in concentrated salt solution. As a result, they lose water, and these mango pieces, they shrivel in size and they convert into pickle. The wilted flowers, they can revive. That means they can become again fresh when placed in fresh water. Osmosis will take place and the wilted flowers can revive again. The meat is preserved by salting. The fruits are preserved by adding sugar to protect against bacterial action. Now what happens? For a bacteria, the salty solution or the sugar solution is not isotonic, and therefore these bacterium, they collapse when they are placed in salty solution or the sugar solution, and therefore the meat is preserved by salting and the fruit is preserved by adding sugar. The carrots, which have become limp, they can also kept in fresh water and they can again regain their normal size. Now why we are giving so much advantages to osmotic pressure? They have a lot of advantages. This question is generally asked for 3 marks and you are supposed to write these 3 points. The very first point, that it is used to calculate the molecular mass of macromolecules like proteins, polymers and other macromolecules like biomolecules. Now why we are using this osmotic pressure for calculation of molecular mass of these biomolecules? Because polymers generally have poor solubility in water, as well as biomolecules, they are comparatively not stable at high temperature, and therefore their molecular mass can be calculated using osmotic pressure. Second point, the pressure is measured at room temperature and molarity is used instead of molality. That becomes the easier calculation. Third point, its magnitude is large as compared to other properties, and all these 3 points makes the osmotic pressure a preferred colligative property as compared to the other colligative properties. The other practical application of osmosis is reverse osmosis, whatever we call as RO. It is also called as desalination of salty water. How it is done? In one container fresh water is taken and in other container salty water is taken. Now what we have studied in osmosis, that generally there is a flow from the solvent molecule towards the salty water. That is the flow of solvent towards the solution. But now in this we are applying pressure on the solution side, which will be greater than the osmotic pressure. As a result, the movement of the solvent molecule will take from the solution towards solvent side, and that's why it is called as reverse osmosis. Therefore, this is used for desalination of seawater. This is the principle behind RO, which is used at our home. The outlet is given so that fresh water can be taken out. the numericals related to osmotic pressure and depression in freezing point will be doing on our next video. Thanks for watching. Have a nice day.